So section 3.6 is about higher order derivatives, and really the big thing to teach you here is notation, because there's not really that much new about higher order derivatives. It just means take another derivative. So a definition, the derivative of the derivative is called the second derivative. Because calculus, as you know, was invented side by two different people, there are two different notations. This notation is the way that the Newton or Euler notation would say second derivative. It would be an F with 2 tick marks. And then this is the Leibniz notation. I really want to point out that this is not a square. This means that we're going to do the operator of taking the derivative twice. It doesn't mean we're going to square anything. So it does look like an exponent, but it means a second derivative, which again is just taking the derivative of the derivative. If I take a derivative of the second derivative, that would be the third derivative. The derivative of the third derivative is the fourth derivative, etc. So I just want to point out that this is the notation for the third derivative, and the Leibniz notation would be, looks like an exponent of 3 but isn't. After 3 tick marks, the Newton form morphs a little bit, so you don't have to keep track of tick marks. They put what looks like an exponent but in parentheses, indicating that that's the fourth derivative. And again, the Leibniz one just looks like it's a fourth derivative. If I want to talk about the nth derivative, I would put an n as that kind of exponent-y thing. So here's an example. I want to find the second derivative of secant. Well, the first derivative of secant is secant tangent, and the second derivative would require me to know that I have to use the product rule. So I'm going to take the derivative of secant, which is secant tangent, and then I'm going to leave tangent alone. For some reason I wrote a t there, and I should have written an x. Now I've lost my pen altogether. And then I'm going to leave secant alone and take the derivative of tangent. With a little bit of factoring, I could take a secant out of both terms. And so there's the second derivative. Second derivative just means do another derivative after you've done one. Again, this notation is the second derivative notation. To make this a little bit easier, I'm going to rewrite it with exponents so I can avoid the quotient rule. So even before I take a derivative, I'm going to rewrite this as 4x minus 3 to the negative 1 power. Now I'm going to take the first derivative, which would be negative 1 times 4x minus 3 to the negative 2 power, and then because of the chain rule, times 4. And then if I want to take a second derivative, that would be negative 4 times 4x minus 3 to the negative third power. Oh, I forgot to multiply by negative 2. Let's start over again. I was trying to simplify and do the derivative at the same time, and that was my downfall. So I'm going to rewrite this as so the derivative would be 8 times 4x minus 3 to the negative third power, and then times 4 because of the chain rule. So in other words, it would be 32 over 4x minus 3 quantity cubed. This notation means the 50th derivative. I don't really want to take this derivative 50 times, but I'm going to go ahead and see if I'll take it a couple times and see if I can see some patterns. So the first derivative would be e to the 2x, and then because of the chain rule, times 2. The second derivative would be e to the 2x times 2 times another 2 because of the chain rule. And so what I notice is that I just keep multiplying another 2 every time. So the 50th derivative would be, well, two derivatives has two 2's, one derivative has one 2. So the 50th derivative would be 2 to the 50th times e to the 2x. These kind of questions are not really asking you to take 50 derivatives. They're asking you to take a bunch of derivatives and see if you can see a pattern. Here's another one. It's asking for the 35th derivative of cosine, and I would recommend that you pause and then restart so you can see how I did it, but you might have another way of doing it. So if I take the first derivative, I get negative sine. If I take the second derivative, I get negative cosine. And if I take the third derivative, I would get positive sine. And if I take the fourth derivative, I get cosine again. And so I just keep kind of cycling through that. So the seventh derivative would be sine, and the eighth derivative would be cosine. So I really want to know, where am I in that cycle if I'm at the 35th derivative? Well, 8 times through the cycle I would be at the 32nd derivative, and so then this would be the 32nd, 33rd, 34th, 35th. So the 35th derivative would be sine of x. The other time that things get a little bit weird is if you're taking second derivatives implicitly. What you do when you're doing second derivatives implicitly is the first thing you do is do the first derivative implicitly. So we're going to do 3x squared plus 3y squared times dy dx equals 0. We're going to solve for dy dx. And I strongly recommend simplifying as much as you can. So we're going to take these 3's and cancel them and get 1 because they divide. And so we have negative x squared over y squared. Now we're going to take the derivative of this to get the second derivative. So the derivative of dy dx is the second derivative. And the derivative of this is going to require us to do chain rule. So we're going to do low d high minus high d low all over the square of what's below. Now we're going to do a substitution because we want our answer in terms of x and y. We don't want our answer in terms of dy dx. So the substitution we're going to make is that we know that dy dx is equal to negative x squared over y. So we're going to make that substitution so that we only have x's and y's in our answer. And then we'll try doing a little simplifying. So I'm going to go over here so I have some space. So then, oops. Got an eraser, I want a pen. So then the second derivative would be, after I make that substitution, negative 2xy squared plus 2x squared y times negative x squared y over y squared all over y to the fourth. I don't like dividing by y squared here because that's like fractions on top of fractions. So I'm going to multiply everything by y squared over y squared to get rid of those fractions over fractions. I'm allowed to do that. That's just multiplying by 1. So then I have negative 2xy to the fourth minus 2x to the fourth. And my y squareds cancel, so I have y over y to the sixth. Yeah. now I'm going to, looking at my numerator, I'm going to factor out a GCF. So the GCF that I see is negative 2x y. And in the denominator I still have y to the 6th. So then I have y to the 3rd plus x to the 3rd. And when I first did this problem, I checked my answer in the back of the book, and it didn't match the answer in the back of the book. The answer to this problem that they had was just negative 2xy over y to the 6th, and they even canceled one of those y's, so they wound up with negative 2x over y to the 5th, and I couldn't figure out why. And then I realized that they made use of this identity and replaced this quantity with 1. I would be totally happy if you stopped at this point. That would be fine. Or if you canceled one of the y's too, that would be great too. But the back of the book just made use of that relationship there. All right. Those are second derivatives. Those are higher order derivatives. You can take second derivatives, you can take third derivatives, and with implicit differentiation, I just really recommend that you simplify your first derivative as much as possible before you take your second derivative, and then don't forget this step where you substitute for dy dx so that you wind up with just x's and y's in your answer. All right, thank you so much.